So in this video I plan to cover a similar problem to the one we covered in the first tutorial with a transverse electromagnetic wave, propagating through space. It's a relatively simple problem. We've seen most of these concepts before. We should be fairly familiar with these at this point, I guess. It's essentially the same as the problem we solved in the first tutorial. The field's different, and you might have a difference. I think it's a little simpler than that first one, so for those of you that were at the first tutorial, you'll know that that problem was a little more complicated than this one. And for those of you that weren't in the tutorials and have never seen any of this stuff before, let's hope we can shed some light on how all this works. So here's the problem, and if at any point you need to use it, I guess you can refer back to the beginning of the video and go back to it. So we're going to jump right in. So what does it tell us? It tells us that we have a transverse electromagnetic wave, so therefore I've written here a TEM problem. So it tells us that the frequency of the thing is 10 megahertz. So we'll write that. It tells us that it's a non-magnetic dielectric. Now non-magnetic automatically tells us that mu equals mu0. Okay. Now at the same time it tells us that HS as a vector is equal to e to the j pi y ax. So right off the bat we know it's propagating in what? It's the negative y, because remember we define e to the minus j as forward, so it's propagating in the negative ay direction. Okay, because in general we define e to the minus j whatever as the forward propagating wave. So we can start solving what it wants us to find. So part A says determine beta. Now we know in general H vector will have some e to the, well, I guess we can call it h naught, e to the j beta, let's say y, ax amps per meter, right? And so if we just directly compare these two results, or these two equations, we compare that with that, and right away we realize that beta equals pi. Units are always important, are radians per meter. And just like that, we're done part A. Okay? Okay. Now, moving on to part B. Part B asks to find the attenuation coefficient. Now, looking at this expression for h of s, we realize that there's only one term. It's e to the j pi y. In the general case, if you recall, I believe we discussed this in the first tutorial. In general, we said that the expression is actually going to be h equals h naught e to the gamma y, or let's say minus ax amps per meter, right? And we defined where gamma is going to be alpha plus j beta. Now beta is our phase constant because it's on the imaginary term, but this real thing here is actually our attenuation coefficient, or constant, whatever you want to call it. Let's call it coefficient. Okay, so if we have that as our attenuation coefficient, then we realize that if gamma is a complex number, not entirely imaginary, so it's complex, there's a real and imaginary part, then in that case we will have some attenuation. And that's usually in the form, if we were to plug that in, let's say, then h would become h naught e to the minus alpha plus j beta y. And so we would have h naught e to the minus alpha y times e to the minus j beta y. And so you see all of a sudden this term here appears if we have attenuation. Now, in our equation, we look at it and we see we have e to the j pi y, and there's no real exponential term. So this exponential term we have here is actually imaginary. Therefore, just by comparing this general case to the case we have, we realize that alpha equals 0. Now, alpha still has a dimension. We'll call it Neppers. It's called Neppers or Napers per meter. And I mean, units aren't all that important when it's 0, but I guess still you always want to include units. So yeah, just by directly comparing and realizing that, you know, the thing is defined in a certain way, we can figure out what this thing is, and it's 0. Right off the bat, you can see that. You probably don't even need to go through all this explanation, but this is for you guys to realize that, you know, there's a reason that it's 0, and I'm not just arbitrarily choosing it to be 0. Now, the next part asks us to find the propagation coefficient, which is gamma. And because of this explanation I just provided in the previous step, so we want to find the propagation constant. And so we say in general, gamma equals alpha plus j beta, but we know that this term is 0, so we have that gamma equals j beta. Beta we found, if you look back up here, is pi, so this is just j pi. Now, what are the units of gamma? You might think radians per meter, but that's actually not true. It's actually inverse meters. And now, how do you remember that? If you think about beta being defined as radians per meter, and then you think about j being defined as an angle, which is in radians, then radians times radians per meter should give you per meter. So now we can go on to part D, and this asks for unit vector of propagation. Now, if you go back to the top, we realize that I've already done this part, I guess, and this is in the minus ay direction because it's e to the positive j pi y, and we define e to the minus j pi y as the forward traveling. So that's quite simple. Now we can go on to E. Part E asks us to find lambda, or the wavelength. So we want to find wavelength. Now, we define beta equals 2 pi over lambda. We know what beta is from the first part of the problem. And so we can rearrange this to find lambda. So if we rearrange lambda equals 2 pi divided by beta, this is going to be 2 pi divided by pi. So we're left with lambda equals 2 meters. I should probably give this one a box as well, then, just to be consistent. Okay, so these are all of our answers in purple. Now, let's move on. Next part, part F. Part F asks for the speed of propagation. You may be tempted to write the speed of light, but we have to realize we're in a dielectric, and so we can't just say c, which is 3 times 10 to the 8. Instead, what we have to do is we can use, I mean, there's a bunch of different ways you can really approach this. I think the simplest way is to say u equals f lambda. We know f, we know lambda. F is 10 times 10 to the 6. Lambda is 2. So this becomes 2 times 10 to the 7 meters per second. Again, not forgetting our units, not forgetting pretty much everything. We have to keep in mind we can lose quite a few marks just for forgetting units. That's part F. Part G. Now this one might be a little tricky if you don't know what it's asking for. It's asking for the polarization of the wave. Now, you might not know what the polarization is. Essentially, the polarization is the way we describe electromagnetic waves. And the sort of convention for describing polarization is using the direction of the electric field. Now, the direction of the electric field is not known to us at the moment because we don't know what the electric field is. But what we do know is we know that this thing, well, let's just draw here first, sort of axis, so we know we have x, y, z. Now we said this thing is propagating in the negative ay, so we say AP, let's say, equals negative ay, and going back to our expression, we know that HS is oscillating, or is entirely a function of x. So let's get that in there as well. And so this is direction of H, S. And so now the thing is, we know based on the fact that it's a transverse electromagnetic wave that it must be, that the electric field must be perpendicular to these two components. So E must be perpendicular to these two vectors. And so therefore we know that it must be somewhere, what are we going to use? Let's use red. No, we've already used it. Let's use green. So we know that E is going to be either up or E is going to be down. So this we'll call E axis. And so therefore we know already, I mean, that's enough information to know the polarization of the wave, because the polarization doesn't ask us which direction, whether it's positive or negative. It just wants to know along which axis. So then the answer to this problem is E is polarized along the z-axis. Therefore, well, I shouldn't say E is polarized. I should say E is oscillating. Therefore, the polarization of the wave is in, or we'll say along the z-axis. So the polarization of the wave, well, the thing to take away from all of this, I guess, is that the polarization of the wave is in the direction of E. And so, I mean, based on our understanding of transverse electromagnetic waves, we can reason that it must be along the z-axis, and in this case I've called it the e-axis, because we know that the electric field will be somewhere will be along that axis, essentially, because we're assuming it's a transverse electromagnetic wave. Now let's move on to part H. Part H? Yes, part H. In this part it asks us to find epsilon r. Now we know it's a non-magnetic dielectric, so all of a sudden we realize that mu equals mu naught, but epsilon might not be epsilon naught in a dielectric, and chances are it's not going to be. That's why it's a dielectric. So what do we do? Where do we start? Okay, so we have a definition for beta, which says omega mu epsilon. Now the thing about this is you're not allowed to use a calculator, so you have to be able to do all of this with pen and paper. But if we apply what we know we have a omega, we know we have a mu naught, and we know we have an epsilon naught, and we know we have an epsilon r. So now what we can do is we can sort of start to take the things that we do know and start to simplify our problem a bit. So we know this is omega, and then we know that this is mu naught epsilon naught, and this is just epsilon r. So I'm just separating. This is mathematical manipulation here. And at the same time, I know that this thing, if you go back to the definition of the speed of light, is just 1 over the speed of light. And so now I can say this is omega over c times epsilon r. And this is beta. So I know beta, I know omega, I know c. So I can find epsilon r. So I can say beta times c divided by omega is epsilon r. And now, so let's go ahead and just do it this way then. Epsilon r is going to be pi times 3 times 10 to the 8 divided by 2 pi times f, we said was 10 times 10 to the 6, so 10 to the 7. And now this whole thing squared. And so now what I can do is I can cancel out this square root, this one. 10 to the 7 gets rid of this 8 and leaves that behind. And so I'm left with 3 over 2 times 10, which is 15 squared. So I have 15 squared, and this is epsilon r. So epsilon r is 15 squared is 225. And 225, this is a relative value, so it's dimensionless, and that is our final answer for epsilon r. Now it asks us in part I to find mu r, or it asks us to find the permeability essentially, so which is the mu r, and we know that since the dielectric is non-magnetic, and I should emphasize that it's non-magnetic, then mu r equals 1 and mu equals mu 0. Okay, and we defined that, like the beginning of the problem, so it's really just asking us what we know about the problem. Now it asks us for part J, the characteristic impedance. Now the characteristic impedance is eta, that funny looking n thing, which a lot of people have called. So eta is actually defined as mu over epsilon under the root. Now if we apply what we know that this is mu naught, we know this is epsilon naught, and we know this is epsilon r. Well, that was kind of bad. And so now we can separate this again like we did in the other case. So we have mu naught over epsilon naught, and this is going to be times 1 over epsilon r under the root. So this term here is actually 120 pi, because that's what the characteristic impedance of free space is. And so what I'm left with is 120 pi times 1 over epsilon r. Well, epsilon r we know is 225. 225 square root. Now if I take the square root of that, it's just 15. If you look back up here, we had this 15 squared here. So it's just going to be 120 pi over 15. 120 pi over 15. Now if you're on a test and you feel that's as far as you want to go, that's fine. If you're feeling a little brave and think you can actually go through and do the division, then let's go ahead and do that, and we get 8 pi. And now the units are ohms because it's a characteristic impedance. So we get that eta equals 8 pi ohms. And that's our final answer for part J. Moving right along, we get to part K now. And so part K asks us for the time domain magnetic field. Now the time domain magnetic field we can determine from the relationship that we already know between the frequency domain and the time domain. Essentially we have Hs is e to the j pi y a x, And we know that in general, we have h is just the real part of h naught e to the j gamma, whatever, let's call it pi, or sorry, y, sorry, and e to the j omega t. And if you recall, in our definitions, we always suppress this term here whenever we're doing our frequency domain calculations, because it's assumed that it's all with the constant frequency, and so we don't really need to carry that term all the time. So now if I compare that to my thing that I have here, h naught is 1, e to the j gamma pi is just e to the j gamma y is just e to the j pi y, and so we can write the exact same type of expression here. So let's go ahead and do that. So I have h naught is just 1, so I'll write 1, and this is e to the j pi y, e to the j omega t. I guess we can go ahead and simplify this as well. So what this actually ends up becoming is just h naught cosine omega t plus gamma y ax amps per meter. So that's what we'd have in the general case. And so now we can simplify it into our case, which is just going to be cosine. We can say omega t plus pi y. This is ax amps per meter. And so this is h as a, let's call it h as a function of y and time. So h as a function of y and time, just to give it a proper sort of expression. And that is part K. Now let's go on to part L. Now this asks to find E, and now in this question it says without Maxwell's equations, which I find kind of silly, because we're teaching a course on electromagnetic theory, but we're not allowed using the fundamentals of electromagnetic theory. So if we want to do it without Maxwell's equations, I don't know, you may recall that ES is defined, well, the relationship between ES and HS, if we're going from E to H at least, is this. AP is the direction of propagation, so in our case that'll be negative y. What we end up getting in our case, so ES equals, eta we said was 8 pi, HS we know is e to the j pi y ax, and what we're going to do is take the cross product of this thing with minus ay, and so the cross product of ax minus ay is going to be minus az. So what we're left with for our expression of Es is minus 8 pi e to the j pi y az, one of the square brackets, volts per meter. Now again, like I said, it's a little silly to ask don't use Maxwell's equations, but since we must, I think the other way to do it, if I'll just write it here on the side. So using ME, I'll call it, just instead of writing Maxwell's equations. If I wanted to use ME, how would I do this? What I would do is, we can do it a couple of ways. We can either use Ampere's law. So I can say the curl of HS is J omega d, right? Because it's in time domain, it's just the derivative of d. And the reason I'm doing it this way is because it's free space. There's no current flowing, right? So I can do this, and what I can do is I can take the curl of H, equate it to d. Let me just write it here and simplify it even further for you. And this will be J omega d equals epsilon e, right? And so I can just take the curl, divide it by j omega epsilon, and I should get the exact same answer. But then you have to remember what the expression for the curl is. So I mean, as long as I guess this way may be simpler. This sort of approach here might be simpler. Assuming you can memorize the equation, but you all know how I feel about memorizing. So in any case, we'll move right along. Part M asks us for the time domain electric field. And so we do the exact same thing we did last time. We consider that e to the j omega t, this thing. So this expression here applies to every real and imaginary, or real and complex, or phasor to time domain, whatever you want to call it. This covers all cases. So any vectors you have that might, have this sort of time or complex dependence, you can use this relationship. So using the exact same relationship, I find that e of yt, because like I said, it's y, it's varying with y, and it also has the time component. In this case, we do have e naught. So this is going to equal the real part of e naught, e to the j beta y, e to the j omega t. And this is going to be in the minus az, right? Well, we'll just say az for now. And then what we'll do is we'll call e naught minus 8. So comparing this with es, we find that e naught, so e naught equals minus 8 pi. And beta we know is pi. So beta we know is pi. Omega we don't really need to substitute in. You can if you want to be, super meticulous and put everything in there. I should put a vector sign there. Don't forget your vector signs, because there are always marks lost for losing vector signs. And so again, we have this thing as 8 pi cos omega t plus beta y is pi y. And this is in the az, and the units are volts per meter. Finally, we come back to M, and we are dealing with the magnetic field in this question. So it asks, what is Hs if alpha equals 0.1? Now you remember that I defined way back up at the top. So we know that gamma equals alpha plus j beta, well, not y, sorry. And we know that in general, Hs is going to be something h naught e to the j gamma y. And so if all of a sudden we introduce alpha, then in our question, gamma is going to be 0.1 plus j pi, right? Because we know beta is already pi. So now what we get, if we look at our question, is we have h in our case, Hs is going to be 1 e to the j gamma y, a x it was? No, yes, ax. Ax, and so we get e to the j 0.1 plus, well no, it's not e to the j, sorry. It's e to the gamma y, it's not e to the j, because the j term is inside that. So this is going to be a to the 0.1 plus j pi y, ax. I just want to make sure that's actually ax. Yeah, that's ax. Okay, and so if I actually separate these two terms, I could e to the 0.1 y, and then I get e to the j pi y, ax amps per meter. And this is Hs. And so now all of a sudden you see we have this attenuation term. This thing here is the attenuation. So what this is asking, essentially, if alpha has a value, then we have is some loss across the medium. So in this case, this would be a lossy dielectric. In just this last little part, though, I should add, the whole thing is not a lossy dielectric. It's only lossy when alpha is some value. So I hope this this sort of problem was helpful. I hope to cover more problems in the future, and they will be posted as I do cover them. If there are any questions, make sure to write them down, and we'll cover them sometime. Cool.